So I will now start with some introduction, giving maybe some overview over the field first before jumping right into the topics. So with that slide, I would like to raise your attention that we are living in a very, very interesting time. You know, if you step back a little bit and look from a historical perspective, so this is the smallest dimension we are able to process, and you know, during thousands of years, nothing happens very explicitly, but then since the 60s, you know, it's going down very rapidly. And you know, Feynman, that's a very famous word. People cited a lot when nanotechnology started. He once said there is plenty of room at the bottom. This was about here, maybe at the beginning of everything. Although I think they would have done it also without saying him this, yeah. Because it was just the semiconductor industry, yeah. And it seems that we are now at the bottom. And we have plenty of room, we have filled out, yeah. You see here some pictures. These are 19 nanometer half pitch structures. So that's, these lines are 19 nanometer wide, 9 nanometer wide. So this is what we can do. This is from ASML, this leading lithography company from Holland. That's one of the highlights in semiconductor industry from Europe is lithography, in fact. You have to know optics, yeah. In fact, the optics uses the theory of this time, of what it was, Ernst Abbe or something like this. Huh? Yeah. So, and of course, you know what it has brought, yeah. I don't know why this is not going anymore. Ah, here, yeah. Thanks to these fine structures, we have now the World Wide Web and a lot of ICs. You know, when I was a boy, just the first transistor radios were available. So you had some transistors in the transistor. I don't know, some cubic centimeters, yeah. Nowadays, on a fingernail, you have 1 billion transistors in a chip, yeah. So, and this allows us all these very nice things. And of course, there is not only the digital world, there is also the analogic world. So I'll just show you one example. I know well this is RF filters for mobile phones. Maybe you have realized that with smartphones, you can now phone wherever you are on the world. In India, Europe, Japan, in the United States, it doesn't care anymore. You know, in the old days, sometimes you had to change the phone because you didn't have the filters, the right filters for the local standards, yeah? Because the standards are made in the United States, in Europe, and in Japan. And I think the rest of the world is taking either of the three. And so it was a very big task of the companies to make RF filters and to downsize them. And here is a very nice example. In fact, was made by Rich Ruby from Avogo. Nowadays, they were swallowed out by Broadcom. Now it's Broadcom, Avogo. So in '95, they have these dielectric filters. Ceramic solutions that here, so relatively big. And so there was the first bioacoustic wave resonator chip coming in 2001 just by this company Avago. You see here the size, and in 2001, and then the same in 2010. It's like this, yeah. And here is enlarged. And nowadays, in fact, you have about in a smartphone, you have up to 60 filters. 60 filters. And I think everything is maybe a cubic centimeter, something like that. So what was once the major part of the mobile phone, meaning the whole RF circuitry, is now a minor part, and the rest, I think, is full with chips and displays and also sensors, yeah, micro speaker and so on. So that's very nice achievement. And I just profit from a talk I heard 2 weeks ago from Bosch. You know, Bosch is one of the major MEMS producer in the world. So they're in fact #1 of MEMS chips producers. And they profited a lot from the fact that they were always in the car industry. And the car industry was the first industry that needed MEMS chips for sensors. And nowadays they're producing 6.5 billion MEMS chips per year. So every week, some 5 million chips, MEMS sensors are leaving the company. And you see here, this is for the car industry, automotive application, first wave. So it's in the 90s, it took off in the 90s to the start. And then the second wave, that's mostly the mobile phone. It's consumer electronics. So the mobile phone has, as you know, accelerometers, gyros, I don't compasses, everything that you know, and it's getting more and more. Also, I mean, the microphones, the loudspeakers are now also going to become MEMS chips, and so that's quite a very nice MEMS package, a smartphone. And then the third wave is coming, this so-called IoT. Now what they understand about IoT, I don't know whether it's a strong definition, but that everything is connected. In fact, this is also the question in this consortium, that everything is connected. So you have your whole household will be connected to your mobile phone in future. So you know everything, what is the refrigerator doing, what is the heating system doing, and so on. What the kids are doing maybe as well, yeah. So this IoT, and of course in manufacturing. I read about this, the fifth generation of mobile networks, yeah, going up to frequencies of 60 gigahertz. So it goes into the millimeter wave stuff. Normally it's just military there, yeah. And in fact, the range of these are very short, but you could fill a room with that. So in fact, you could control complicated machines, not by wires, but by the mobile network. So these ideas, this also represented in this project, this idea for a car. But this seems to be a general concept. I heard that you you connect it by wireless, and you go to this, I don't know, 20 to 60 gigahertz bands of the fifth generation, and you control a machine. So some first developments are going on in this direction. Well, so this means, but this also means, what I would say, of course, not everything is digital, as you can already see with this input from Bosch. We need a lot of sensors, and of course, a lot of electromechanical transducers are needed, because finally, wherever you would like to do something, you need mechanics, yeah? Because without mechanics, everything would be static. Yeah? And so only mechanics make something that moves, yeah? And that transmits, for instance, material or handles such things. Yeah? So to make robots. And when you think about what means electromechanical transducer, you have mechanical inputs and outputs on one side, and electrical inputs and outputs on the other side. And you need a device that is making the conversion. And as we know, of course, piezoelectricity makes this conversion. So that's a material solution. Yeah? A part of artificial solution, like electrostatic attraction or pistons with vapor or something like this. Yeah? As we have also heard yesterday about. And let's say the materials that have strongest piezoelectric effect are of this PCT family, so perovskites with oxygen actuated, and they have a 4+ ion here in the center and then lead in the corners. So that's still the strongest material. There are also, how to say, derivations of that, like PMN and PT. You play around with the ions that are in the center. You mix niobium and magnesium and so on. That gives stronger materials, but it's always the same family. And this is the standard actuator you buy, let's say, from Physikinstrumente. You buy a linear actuator. Of course, it's made with that, except if you wish. I think they have one product lead-free. You have to put some more voltage for the same stroke, but they have one. But okay, so that's this material. And then also we'll speak about this aluminum nitride. This aluminum nitride is not a ferroelectric like PCT. It's a very stable material. It's polar. and it's only used in thin film form for piezoelectric applications. It exists as ceramics as well. You know for what application ALN is used as ceramics? Anybody an idea? No? That's in electronics. It can be used as substrate because aluminum nitride is a relatively good heat conductor. You know, alumina is not as good as aluminum nitride. And glass is very bad heat conductor, yeah? So there where they need better cooling of ceramic substrates, they can use aluminum nitride. Of course, you see it's close to diamond. You know, that has a Wurtzite structure, but this is somehow also similar to zinc blende. And zinc blende is just a form of diamond with two atoms, yeah? So these little ions in the corner around carbon, yeah, they are sometimes good heat conductors and also very hard, yeah. And because it's mechanically very good material, it can be used to make resonances in the microwave region. You see here symbolized a thin film that is driven in parallel plate electrode system. And what one does is one makes a thickness mode resonance. And you see here the thickness mode resonance in the admittance. So you measure the admittance or also the impedance alternatively. And you see here, this is in fact, the capacitance here, or the susceptance here. Yeah. This comes out from the capacity. And you see this very nice resonance, and here is the conductance. And so that's usually, you have a peak in conductance at the resonance, and this kind of dispersive relation in the imaginary part. Okay, so important here, just to remember, is that it goes to the negative side. So, you know, it's a capacitor, so has the admittance is positive, yeah, imaginary part. But here is a negative side, so here plays a coil. And when you have a capacitance, a coil, you can make a filter and a resonator. So these filters. Yeah, we will hear later more about the piezoelectric effect, but you can simply think about this. So what is piezoelectricity? You have a direct effect and a converse effect. The direct effect gives you an electrical parameter here, the dielectric displacement field, electric displacement field as a function of stress. I use here mostly the abbreviation proposed by IEEE, meaning T for stress and S for strain. I know that in mechanics, of course, you're using sigma for stress and epsilon for strain, but in electromechanics, that's the problem that one has also all the abbreviations for dielectric constant is often epsilon, and the conductivity, specific conductivity is often sigma, and to avoid all this confusion, they have proposed to use T for stress and S for strain. Yeah, so that's and this T is a piezoelectric tensors. It's a third rank tensor because this is second rank, this is a vector, so it must be a third rank tensor. There is a material imposed, a condition imposed, there must be no inversion symmetry. There is also electrorestriction as a general phenomenon, which sometimes, well, it's also, there are some people claiming that some materials have a giant electrorestriction, but okay. The strain is here proportional to E squared, and you note that there is no inverse of that effect, so there is, you cannot make an electric field with a strain with this effect. Huh? There is no square root laws in nature. You know, you cannot turn this around, so you can only use it as an actuator. And there is also what is a lot discussed during the, let's say, last 12 years or so. It's also the flexoelectricity. So when you have a gradient in the material, you can also have some effects, and which are also not depending on absence of inversion, because this is a 4-rank tensor, and this is invariant under inversion. You know, when you have a inversion, you know, we have every how to say component changes the sign. So this transforms like product of x, y, z, and something to the 4, or x1, x2, x3, x4, or something like that. And so with the inversion, this doesn't change. There's also the inverse effect, because you can have a d-gradient producing a strain. That's also possible. Okay, so that's the piezoelectricity. So it's a much stronger effect, much more easy to understand, and on larger dimensions, totally dominating. This can only be of importance at very, very thin films. So in ALN, what is special? This is, yeah, you see the dancing ion. So the ion motions, in fact, in a piezoelectric material generate a wave. And for ALN, which is a very stable material, is very fast. In theory, you could go up to 100 gigahertz, something like this. The Q factor, I mean, the quality factor will not be as great as anymore as at 2 gigahertz, but you can go very high frequencies. In practice, I think we should stop at 20 gigahertz. But in practice, we go. Very strong forces. You need relatively low voltage, high energy density, and so on. So totally linear effect, really totally low noise, high mechanical quality. So that's why they like it for RF. And you see how this looks like in reality in many chips. Instead of insulating the film with a vacuum gap or air gap on both sides, you can also use a mirror, an acoustic mirror. It's called a Bragg mirror or so. It works like in optics. Maybe you know in optics you can make dielectric mirrors. Maybe you have heard about this. You make a sequence of lambda quarter layers with high and low refractive index, and this will reflect the wave. You can do the same trick in acoustics. So the refractive index is then played by the acoustic impedance and make such mirror. So this is such kind of mirror, silicon dioxide and tungsten. You need a low impedance is silicon dioxide, and tungsten is a high impedance material. Yeah? And to make such kind of things. You see here again this example. What is the leader in filters is the so-called double-X filter. And there you have, in fact, two bands close to each other. One to transmit, meaning you send out waves here, and you receive waves here. And since they are so close, you need a very, very big rejection in the middle, so that wave going out is not blocking the whole reception channel. And that's why you need filters that are very steeply going down here, 60 dB. And so this is done with especially this one with aluminum nitride, thin film bulk acoustic wave resonator. The reason is also that aluminum nitride is a good heat conductor, so you can put more power. Yeah. So you see, in fact, that also this is a point that is important for this material. Now, if you look at the whole picture of piezoelectric materials, we have, for instance, mechanical stimulus, make a sensor, electrical signal goes out. This typically for vibration sound sensors and motion sensors. We have the opposite direction, electrical stimulus and then displacement, precision and fast actuators. So all atomic force microscopes are, in fact, the tip is actuated by, or the substrate, one of the two, is actuated by PCT actuator. Then we have also vibration energy harvesting buses, yeah, that comes from here. Mechanical power, electrical power is vibration energy harvesting. In the other direction, you have buzzers, the singing letters. Yeah, I don't know whether it's still PCT, but years ago this was involved. PCT, yeah, that you open the letter and then some music is coming. Yeah, so this ultrasound cleaning, that's also a very good application. And then we have transducers which go in both directions, so it's required that you go in both directions. This gives nice resonators and transducers. Medical ultrasound imaging, it's about 3-5 megahertz to look through the body, and 10-20 megahertz to look into the eye or artery walls or something like that. So that's at least RF filters I'm speaking. Oscillators for time control. I mean, you know the quartz. Everybody knows quartz, unbeatable oscillator for many purposes. People try to beat it, but still, you know, with MEMS. Doped silicon, heavily doped silicon structure seems to have approximately as low time drifts or frequency drifts as quartz, but quartz is unbeatable with respect to very low price and very high stability. So that's, yeah. Now in thin films, what we can do, I tried to put that on the frequency axis. What is very special with the piezoelectric effect is that you have an immense frequency range. Yeah. In fact, from DC to, as I told you, 10 to the 10 hertz about, and then you have many different modes at very low frequency. I mean, these flexural structures are dominating, so that's also for the energy harvesting is the major part. You put piezoelectric film on some membrane or cantilever or beam or whatever, or bridge, and then it's deflecting, so you can do that. I mean, it cannot be too big, yeah? I mean, one thing of downscaling means always that the frequencies go up, yeah? So when you make something very small, you cannot do it at the same time very slow. So, but let's say you can go down to, well, what was said here, at least 100 hertz, and yeah. You can also make contour mode resonators, so resonators that use a transverse piezoelectric effect to make plates vibrating in this sense. You can do resonators at, let's say, 100 megahertz, something like that. These are called contour mode. Then you can make waves, lamp waves. There are various types. This is the basic asymmetric mode. So this is a wave like this in a membrane. You can go down in frequency to maybe hundreds of kilohertz and up to megahertz or so. Then there are more complicated line waves where you also have thickness mode coupling and this coupling, and they go up to gigahertz, whatever you want. And this is then the thickness mode, the TF bar. So that's, yeah, I put here some applications. Yeah. About applications, inkjet printing heads. This is also on the market now, and so. Yeah. Yeah, so here I would like to point out that many of the advantages, of course, not only because of the silicon MEMS chip has made a lot of advancements. What has made a lot of advances is the packaging. This is in fact as well. So you know that nowadays you can mount a package on top of silicon chip on silicon package and so on. So that everything becomes more and more closed. Yeah. Yeah, here about scaling of these effects. For instance, in the bioacoustic wave resonator, when you look at the frequency, which is, let's say, 1 over the wavelengths, and so what is the frequency depending on the thickness H here? So you have the resonance frequency here, the thickness, and when it's very thin, you know, we go to gigahertz frequencies, you have a thin film. Here, in megahertz range here, you have to have bulk materials, several hundred micrometer thick. So here we have bulk materials, then there's a range that is suitable for thick film technology. Multi-layers with thick films of PCT can be done here, and then we have this thin film range. Yeah? So that's it. Yeah. Important to see when using thin films in MEMS or in mechanics is that the fact that, of course, the substrate plays a big role. I mean, the frequency behavior is mostly dictated by the substrate and the dimensions. So you can tailor the length of a cantilever, and this gives then the frequency. Yeah. the frequency of a cantilever is basic mode is about the thickness divided by the length squared. So you can tailor your system with mostly the passive part, elastic passive part, and PZT or the other piezoelectric film will just modify somewhat this frequency behavior. You can use the direct effect for sensors and vibration energy harvesters, the converse effect for many other, let's say, for a micro speaker, or so for a mobile phone. There should be one product coming in this direction, or for an active lens and so on. So there are many possible applications. I will mainly speak about these. So we have always the Wurtzite ELN as a, let's say, the hard material, and then the perovskites family is more soft, ferroelectric, internal polarization, and about ferroelectrics. Ferroelectrics usually have a phase transition at some point. So when you cool down from high temperature, then you have somewhere a phase transition and coming to the ferroelectric phase. So above it's paraelectric, it's not piezoelectric, then below it's piezoelectric. You have many domain issues. And the fact that we have ceramics of PCT and that the ceramics is piezoelectric is due to the fact that we can align the originally random domain pattern here with a polling process, and then we can have ferroelectric materials in ceramic form that are piezoelectric after polling process. With ALN you cannot do that. ALN is not ferroelectric, and so you cannot change the polar axis of the crystals. So ALN in ceramics is not piezoelectric. That's a privilege of the ferroelectrics to have this. Yeah. However, when you go to thin films, you have the chance to make thin films textured. So you can grow thin films in a textured way and to align all the polar axes in the same sense of all the grains. And then ALN can be piezoelectric. So this is the art of doing this. By the way, also in the ferroelectric materials, there's also the question, can you beat the random orientation in ferroelectric materials with textured films? Normally we would say yes, we can do that, because piezoelectric effect is anisotropic, so you will find the optimal orientation of the grains to do that. Yeah. Now it's working. Oh, yeah. Just to speak a little bit about the basics about the perovskites. So I explained already the structure. These domain patterns that appear below the critical temperature, below the Curie temperature, are in thin films quite important, because here is an example of tetragonal film, and you see here 90-degree domains. And so in A we say they call this is A domain, polarization is horizontal, in C domains it's vertical. So that's a famous pattern like that. So here and the other is here. They interact elastically with the substrate, so this is an important topic. And so you cannot choose the domain patterns as you would like to have sometimes, because the stress they generate interacts with the substrate, or the substrate stress interacts with the ferroelectric material. And so there is an optimal solution for zero stress. And so that's why you cannot freely choose, let's say, saying, well, I would like to have only C orientation. You can do that on specific substrates. Unfortunately, this is not silicon. It's normally not silicon. But on specific, of course, you can use strontium titanate. You can use lanthan aluminium substrate. You can do that. Yeah. So that's one of the complications you have to think in your work. I mean, it's very good always to start, let's say, with new materials, new processes to make epitaxial film, because it helps to grow the film. Yeah. That's very good, and you're much faster in the target with your film. Yeah? But then if you would like to put it into silicon, you have to make some adaptations and conceive integration and so on. That's in the second story. That's the second story. Yeah. PZT also has phase transition, so as a function of composition, so you can choose zirconium-rich composition or titanium-rich composition. Here it's tetragonal, here it's rhombohedral, and the peak properties are always at or around the so-called morphotropic phase boundary. Yeah? So MPB abbreviated, morphotropic phase boundary, which is here. Yeah. I don't know. Here you see some examples of ferroelectric properties. The most prominent one is, of course, hysteresis loop of polarization. So when you sweep the electric field in such a capacitor here, you find this polarization loop. We go up and go down. And this allows you to measure the polarization and the Corsi field. The Corsi field here is very small. It's about 50 or so kilowatt per centimeter. When you measure the capacitance as a function of superimposed DC field, yeah, you know the capacitance you measure normally with a small signal, small voltage excitation. So it's the small signal response to a small AC electric field, yeah, and you measure the charge that is coming as also a sinus, and you calculate the capacitance, and you can superimpose a DC field. So then you have a DC field plus the little AC excitation, and you see then how the small signal response changes with applied DC. Here is a dielectric. Loss because there's a friction. So you are ELN, your per mil region. One per mil, or even less. So that's a very big difference as well. And when you would like to use it as an actuator, so you apply an electric field and you check about the stress that is caused by in the plane of this film. And you see that you have two branches, but they're all going up. So the stress inside the film plane is always tensile, except for this little stuff here, where it but this is a dangerous operation mode because then it switches then up to the other side. Yeah, so that's not very good. So you have this, and also it's not symmetric because I mean also the film is not symmetric. You know, the film starts growing at the bottom and ends on the top, and this is not a symmetric situation. So in fact you always have broken symmetry, and you see that also in the properties. Right, ferroelectrics are like a living material. So very complicated. Yeah. No, this is the same thing. So, just to compare these materials qualitatively, so we have now, let's say in industry, we have these two materials. When you are sent to invent new materials and to develop new materials, but what is now the standard is to have ALN for high frequency, radio frequency applications, yeah, and PZT for lower frequency applications like inkjet printer, focus lens, what is coming, micro loudspeaker for mobile phones, then also the thing is, what I see, the microphone for mobile phones will come with ALN, aluminum scanning nitride. Very, very key. There's a company in California as well that's working on So, I mean, this material is very strong in the stroke. So when for actuators, this is better than that. It has some hysteretic behavior. It's not, it contains lead, so this is criticized by many people. That's why you can read titles like lead-free barium titanate. And they said, why? It's clear that barium titanate is lead-free. But this to underline that the piezoelectric material with no lead. Okay. You see also the properties change. So when the dielectric constant and losses increase by 100 to 200 when you go from left to right, and but also the piezoelectric coefficients they increase by 20 to 30 when you go from left to right. So this is justifying the existence of PCT. Anyhow, I mean, medical imaging you couldn't do without PCT. I mean, you need a very good contrast, very strong material. People working to replace it by electrostatic sensors, the so-called CMAT, capacitive micromachine ultrasonic transducer. They're trying hard since 20 years. So I don't know whether they will manage it. Maybe some parts of the probes maybe could be. Okay. Yeah, so that's a summary on properties. You know, you compare two materials, that is PCT and that is aluminum scandium nitride, or aluminum nitride. So this is the solution now. If you would like to have stability, linearity, you have to stick with those two. If you would like to have a lot of stroke and force, you have to go to them. So that's a solution. I think you will speak about this. Huh? Yeah, I mean that's just a classification of materials. I think I don't know, where you are in your. We have the piezoelectric materials. All piezoelectric materials, they have no inversion centers or crystalline materials, and as representative material in this type of materials that has only the absence of inversion centers that makes it piezoelectric is quartz. Quartz, very interesting material, discovered about 1880 to be piezoelectric. Very soon after the discovery of the piezoelectric effect, quartz was already discovered. First device is 1920. Caddy. Then we have the polar piezoelectric material. So piezoelectric means that you have a polarization that is temperature dependent, and this means when you change temperature, polarization changes, so you can detect the charge. So these are called piezoelectric or polar. The irony is that these materials that are here, like airline, etc., are very bad piezoelectric materials. That's why I often prefer to say it's polar material, and not piezoelectric. But the custom is to say it's piezoelectric. And then inside of the ferroelectric materials, they have all these properties, plus they can switch the polarization. So the definition must be that you can switch polarization by an external field, and they're called ferroelectric. And maybe the piezoelectric, you have them sometimes in infrared detectors. I think still in many vacuum tools, you will find contactless pyrometric temperature sensors. So it's one of the standards there, in fact. But for infrared imaging, they lost the battle. It's much cheaper to make some sensors based on semiconductors, which have a very strong resistance variation with temperature. Semiconductors do have that, and if you can do that in a low noise stuff, then you can make it like that. Yeah. Okay. So now if you compare piezoelectric in a rough way with the competing principles, for instance, we can say, well, we consider power consumption and speed, or drive voltage and speed. So speed is an important parameter. And so in this game here, you know that there are also shape memory alloys. You can have very strong strains when you change temperature around some critical temperature. And so if you compare that, of course, I mean, they They're very slow, they have a high power consumption, they're not good, and piezo and electrostatic principles are very fast, low power. And with the drive voltage, then we can differentiate these two. Electrostatic also needs much more voltage, because it's basically a very weak effect. Yeah? You know, it's epsilon equal 1 in electrostatic actuators, whereas PCT is epsilon equal 1,500. And this makes a big difference, and also it reduces the voltage. You know, that's, yeah. In fact, electrostatic actuators you don't have in the macro world, because you would need thousands of volts, and this is very dangerous. But in the nano world, you know, if you have a gap of 10 nanometer, I mean, you need maybe 10 volts. That's very good. Yeah. Okay. So you see the advantage piezoelectrics will never die. And then here I have a comment. It's maybe interesting for you as or for PhD students at least. Why does it take so long? So I traced here the history of, let's say, zinc oxide aluminide family. There were some guys, Fred Hickerdale, for instance, they tried to make zinc oxide films and also later iron films starting mid-60s. Yeah? And, and here the first idea, what it is good for. Yeah? And the idea we could make thickness mode resonators. Yeah? This was 1980 or 1979. Two groups, one from the United States, one from Japan, proposed to have these thin film bioacoustic wave resonators. And then nothing happens. Nothing happens. And then at this time, there were some people like Lakin, who had a little, he was professor of MIT, and then found his own company working exclusively for the American military. You know, the American military is a very good technology driver because they always know what they need. Yeah? And if they see something, they say, that's interesting, we pay. No? So Lakin made special filters, let's say at 5.3 gigahertz or 2.7 gigahertz or something like that. Nobody else could do. So and then also one of his pupils, he was working for HP. Rich Ruby said, well, we would like to have it, secret industry development. I didn't know that they are working on that until 2000, and then said, well, we have a product. And then they came out with a radio frequency filter, this duplex filter I was showing. You see, and so from the moment you have knowledge about material and knowledge about an application of the device, it goes 20 years until it comes on the market. 20 years, yeah. Of course, it's what did the people do in the meantime? Of course, there was a lot of success. In the meantime, the spatter deposition was very much developed. You know, in the 80s, people invented the rotating magnetic field, spatter sources, and so, and people had awfully stress in these films. And this was then solved with the technology in the 90s. How does stress depend on process condition? How you can marry good piezoelectric properties with low stress, and so on. So that's where we. Yeah, you know, this is not, and also nobody was interested in making filters at 2 gigahertz. Thin films cannot make filters at TV frequencies. So TV goes up to 400 megahertz. Yeah. So, and if you would make a film for 400 megahertz, it would be so thick, I think it will jump away from the substrate on its own. Yeah, yeah. So it's impossible. And people found a very good solution. These were surface acoustic wave devices, and there it's just the lithography that determines the frequency. You take a lithium niobate crystal, piezoelectric crystal, and you make an integrated electrode system, and you define the surface acoustic wave frequency there. And so it's a very excellent solution. So you don't need thin films with thickness mode resonators. So it only became interesting. The mobile phone standard went to 2 gigahertz. Yeah, not before. Even the GSM frequency in this time of 900 megahertz was not interesting. So you see, you also the application must come. Huh? And what I find a miracle is that there's always an application coming. Yeah, that's very interesting. So you can do something, and even so, there is no application, Nobody said, that's not useful. Nevertheless, you never know, maybe 20 years later, people find it very interesting and will do it. The problem is for patents, you have great ideas, you would like to make a patent, but then 20 years later, it has no value. It's a little bit the problem, yeah. So, exactly. So, I had many good ideas in this time, but, now it's coming, but anyhow, it would have not served to anybody, yeah. So, that's... and in PCT, it's very similar. So people started to make first piezoelectric films in 1980, and in 1990, the first, let's say, very primitive demonstrator that it could be useful for MEMS. So it was simply a PCT membrane, and it was vibrating, and you see why it was bubbling. So, very interesting. It's bubbling around, and you put powder or so, then powder is shaking. So something like this. And here micromotors and so on. I don't know whether it can. I think we'll show it later. Yeah, that's also something. Everybody was interested in micromotors at the beginning of MEMS. Also here in Besançon, some people were working on micromotors because this was fascinating. When you could show that something turning, rotating, this, has idea with the micro robot, the submarine in your blood, and so on. All these ideas that fascinated people very much. But at the end, it was announced is an inkjet printer. So you just have a membrane pushing a pressure on your inkjet. How do you say ink reserve, and kicking out drop. So that's this is a micro tsunami. Yeah, that's why this comes from Japan. So the leading companies in this field are Panasonic and Epson. Yeah, and now there's also an English company. They are specialized in coloring tiles, carrelage. Also, you would have this idea maybe, but of course a very good idea. You can print your picture on the tiles, yeah, and then you have in your bathroom you have a picture of something, and and this you can make with inkjet, yeah. So before burning the tiles, you do that, yeah, and they're working also on the inkjet. So this also coming. It's very interesting. So and also you see here it's about 20 years or maybe even 25 years because it's more complicated than aluminum nitride. Yeah, it's like now it's a membrane that we did in fact for a printer company OC of Holland. They also wanted to start, and we started something, but they never advanced really. If you are interested in something and convinced about something, you have to motivate industry to advance. And then they kicked us out because said, well, you're working on 100 millimeter wafers. We don't like that. We would like to have 150 millimeter wafers. And they missed a good occasion because, it doesn't matter the wafer size. And basically, you have to learn the technology. Yeah, okay. And this is also illustrating. I once made the work to collect everything I found about this transverse piezoelectric coefficient, this one. And so this was our work or from other people. Sol gel deposition, how the coefficient went up. This was epitaxial. It's not quite clear why epitaxial films do not make so much progress. I think it has to do with mechanical constraint of these. That's PCT, that's PMN-PT. The word first sol gel, and then some guy was coming, or some people were coming with ferritic, with spattered films, epitaxial ones, yeah? And so that's now spattered films as well, that's spattered film as well. So, also this took time, so this is also about ideas, how to improve all the things, yeah. Yeah, so basically, we had the Swiss connection, Japanese connection, That's Penn State connection. You know, that's also Penn State. Yeah. That's Norway. SINTEF is also very active in this field. Yeah. And just to have an overview of materials from the point of view of properties, generally speaking, we have these materials. Yeah, so quartz, it's evergreen, so to speak, single crystal. You know, it has no polar axis, so we cannot have ceramics. So we must have single crystal. And what is also very ironic, nature can do it. So what happens is you have some quartz mines, for instance in Brazil or so. And they get this quartz and then they cut it into thousands of pieces, and then they grow crystals out of the seeds from the natural quartz. And they make then up to 5 generations of this. And then after 5 generations, the quality is not good enough anymore. Too many defects. Yeah. So it's amazing. Very small coupling, but excellent stability, Q factor, and low. It's a world champion in low thermal drift. You cannot use it above 500 degrees.